In this video, I will show you how to use Epsilon Aero data and Epsilon access filters. The test case I will use for this demo can be found in the Epsilon website. Go to Open Data, and then I will use the NACA 12 airfield case. Just click on here and you will download the case. So, go to ParaView, click on Open, then select the case file, not the data file, just the case file, click on OK. Then you have to specify the file format, in this case a Fluent case file, click on OK, and wait some seconds until ParaView reaches the mesh. So, click on Apply, and wait again some seconds until ParaView displays the mesh. So that's all. Now you have the data on ParaView. The next step is to apply a filter called Merge Blocks. Go to Filter, Alphabetical, Merge Blocks. Click on Apply. This step is necessary because Epsilon works only with single block cells, and the Fluent case is a multi-block cells. So that's why we need these merge blocks. So make sure that this is blue. If it's blue, that means it's active. Go to Filters, Epsilon, Epsilon Aero Data. And this is the interface you have to properly set up before clicking on Apply. The first parameter is script. You can ignore it if you already follow the installation procedure. So go straight to Input Data. In Input Data, you have to specify first the data format. This is a Fluent case file, but you can select the proper file that you have loaded into ParaView. The second parameter is to specify the outwards direction. If this is the mesh, this is the outwards direction. In this case, it's given by the y-axis. So I will retain y-axis, but you can select either the y or z axis. The second part is the most important because it will define the upstream reference values. In my case, I have a 10 degrees angle of attack, static pressure, and I have the core there. So the data that you download from our site already contains all the parameters you need. But if not, you have those parameters from your CFD data. So angle of attack, in my case, is 10. Since this is a 2D simulation, the angle of side slip would be 0. Then you have to specify the airspeed type, either Mach number or velocity. In my case, I know the Mach number, so it's 0.3. Then you have to specify the pressure and temperature, and this can be defined as total or static values. In my case, I know the static values, and I will retain these default values. Finally, I have to define the reference surface. If this is a 2D case, you don't need the reference surface, you have to specify the chord instead. Why? Because it considers that the depth is unitary. So the chord is 0.435, and that's all. These input data and upstream reference values are the parameters that you have to modify it every time you apply the Epsilon Aero data. The remaining parameters output options are not mandatory. So click on Apply and wait some seconds until Epsilon Aero data executes the Python file. So the first thing you have to observe are the output messages. Click here and drag upwards in order to see the entire window. The first part you can ignore. Maybe you can see some errors in red there. Just don't pay attention to that. That's normal. What you have to read is from the green part downwards, and particularly the part called output info. The first thing, it says that it's a Fluent file. It recognizes that you have loaded a Fluent file, and more particularly a 2D data. Then you have a reminder. In this case, it reminds you that you have selected the non-dimensionalized parameter. And finally, it specifies the normal direction to use for the slice plane. Later, in another video, I will show you how to use these parameters. So far, you should have to know that these are the cosines director of the normal of the sorbet plane that you will use to analyze the wake. Then I go back to the output options. By default, all these parameters are checked. Non-dimensionalized means that the output values, for example, drag, is non-dimensionalized. It will be shown as a drag coefficient. If unchecked, it will be displayed in newtons, or if, for example, you select exergy parameters, they will be displayed in watts. Then, aerodynamic parameters near-field, far-field methods, exergy, and lamp vector are all the analysis methods that you can select for the output. If all of them are checked and you click on apply, you will have plenty of output parameters, as you can see here, and they are grouped based on the parameter you select here. For example, if you selected the aerodynamic parameters, you will have all the aero parameters grouped with the word aero before. So let's analyze one of the outputs of Epsilon Aero data. Go to solid color, click on the drop-down list, and then select the parameter that you want. In this case, I will analyze the U velocity along the aerodynamic x-axis. Then make sure that this icon is in 3D. This will simplify the interaction of the mouse with the geometry. Now, this is the velocity component along the aerodynamic x-axis. However, you have here the mesh axis, and this is not coincident with the aerodynamic axis. So you have to display the aerodynamic axis. That can be achieved by using another filter called Epsilon axis. Go to Filters, Epsilon axis. Click on Apply, and by default, it creates 3 arrows that represent the new reference system, the aerodynamic reference system. I will turn on again Epsilon Aero data, and I will reduce the size of the arrows. By default, the size of the arrows is 1 meter. I will reduce that to 0.1. And now I have to change the color. The color of the arrows by default is gray, but you can change that to colors. And if that's the case, they have the same color code that the mesh axis. That is, the aerodynamic x-axis is in red, as well as the mesh x-axis. The y-axis is in yellow, as here, and the z-axis is in green, as here. As you can see, the aerodynamic axis is different from the mesh axis. In this case, the x-axis, the aerodynamic x-axis, forms a 10-degree angle with the mesh x-axis. On the other hand, the y-axis this time points normal to the surface, whereas in the mesh case it points upwards. And finally, the aerodynamic z-axis points normal to the upstream flow direction, whereas in the mesh case it points normal to the plane. That's why this mesh is useless for the analysis of the U velocity. For the U velocity or any other velocity component, you have to use the aerodynamic axis. And this is all you have to know to use Epsilon Aero data and Epsilon axis.